Hello all, and welcome to this session. This is SRV317, Unlocking High-Performance Computing for Financial Services with Serverless Compute. My name is Harsha Nipani. I'm a Solutions Architect with AWS. And it's my pleasure to welcome Ms. Bin Liu from Fannie Mae. She's a Senior Director of Risk Modeling and Analytics. She has over 20 years of experience developing high-performance computing using large-scale Monte Carlo simulation at Fannie Mae. And this particular use case was developed by Ben and her colleague John Simon, who is also in the room, to essentially develop a Monte Carlo simulation on AWS as the industry's first simulation using AWS Lambda. Okay. Thank you. All right, just to level set, we're going to first review the session objectives. This is an advanced level session. I'm assuming you have background on AWS services, particularly Lambda and S3, because we're going to be talking about Lambda, a great deal of Lambda. But in case you are not familiar with this service, I will certainly give you an overview and then dive into the session details. There are three segments in this session. The first segment is we'll review the grid computing architecture, some of the use cases of HPC, and then I will set the stage for Bin Liu to walk us through Fannie Mae's use case of how Monte Carlo simulations were executed on AWS using Lambda. And then the final segment will be a live demo of Lambda functions using the MapReduce framework. Right, let's get started. Overview, this is the segment one, where we'll be reviewing HPC and grid computing framework and how to implement such framework on AWS. HPC, high-performance computing, is a framework that allows users to solve complex business problems for which applications require large amounts of compute infrastructure to power these application workloads. The high-performance computing world is evolving continually and rapidly, and the main motivation here, the main driver here is both economics and also technical. As HPC systems are executing large amount of computations, there is a need for a large scale of compute resources that are required to execute these jobs. But also, applications now have ability to not only scale out and also ability to have high scale, performant, and low cost infrastructure access when you extend this framework into the cloud environment. Why is it important for customers to have this capability where they can extend the grid computing framework into the cloud? Because workloads, particularly HPC and grid computing workloads, require massive amounts of parallel computing architecture requirements. And especially in the financial services industry, customers need the grid computing framework that can tolerate some latency and should be resilient, but the optimization is more focused at overall throughput using compute grid. So that is some of the characteristics of HPC implementation on grid. Many organizations are now also looking to new ways to perform compute-intensive operations, compute-intensive tasks at a lower cost. So that is a significant driver for many customers. And AWS provides virtually unlimited compute and storage options for providing such a framework and the capacity to launch on-demand resources and ability to auto-scale provision resources on the fly and essentially ability to have resources that fits your compute requirements and just have enough capacity without the need to worry about either idle time or lack of capacity with the compute grid, right? So with that being said, now let's talk about some of the use cases of HPC and some of the implementations of HPC. At a very high level, there are two variants of HPC. There is a cluster HPC and there is a grid HPC that you could implement. There are two significant differences between the two when you start implementing these. Cluster computing and grid computing are two flavors of computing standards that do support HPC parallelism, right? On the left side, you see HPC clusters. These are for application workloads that require tightly coupled integrations, and there are latency sensitive applications. They tend to use cluster HPC more often. And some of the characteristics for cluster HPC is you essentially need to have access to your compute infrastructure that is typically in the form of EC2 instances that can be leveraged. Again, a lot of variations within EC2, right? You have the compute optimized, you have the storage optimized, there are accelerated compute options in EC2, and then again, with the latest generation of EC2 instances, you could also have Intel Xeon processors, essentially with advanced floating point operations that can be implemented, encrypt data at rest, right, and boost your processor clock rate for peak loads. So with some configuration tweaks, like for example, you could do placement groups and enhanced networking. Placement groups are important where if you have requirements for running HPC compute where there is a lot of data traffic going between the compute nodes and the storage, underlying storage devices, then you would obviously have the proximity matters because why does proximity matters in HPC clusters? Because you want to reduce your latency and jitter when multiple task nodes are coordinating the tasks to run HPC. On the other side of the equation, which is the focus of this session, there is grid HPC. Grid HPC is different in the sense that these are loosely coupled parallel infrastructure, right? It is not as latency sensitive as cluster HPCs are. However, you need to be able to have scaling ability, both scale out and scale in ability, and also obviously which will reduce costs when compared to running a steady state application like a cluster HPC, right? And state is very important. If you have workloads that have state information that needs to be implemented, then implementing grid HPC with serverless Lambda, you would have to make sure you have state written into persistent storage, either S3 or Dynamo, to make sure that persistent state information is acquired by the next processing worker. So that is the key difference there, these are loosely coupled applications that are mostly suitable for grid HPC. And also, if you have any state information that requires, as part of your processing workload, you need to write your state to persistent storage. So that's the key differences. And then there is also a variation that we have seen in the industry where you could technically have a grid of clusters. Essentially, what you're going to have is you're using a grid strategy to implement parallelism, parallel workloads, coordinated through cluster HPCs, right? So that's the third option. But mostly, it is either the cluster HPC workloads or grid HPC, and the focus of this session will be grid HPC. All right, now that we have reviewed HPC workloads, now let's look into how grid computing is implemented across financial services industry. And this is not, by the way, when I say grid computing implementation, this is not specific to financial services only. This is extendable to pretty much any workload that has these certain characteristics. We are going to talk about what are the grid computing characteristics later during the session. But for financial services institutions, the core concepts with some of the workloads are financial simulations are essential to the operations of financial services institutions, right? They need to be able to do a lot of simulations based on the market feeds and able to manage. Why do they need to do simulations? Because they have to identify risks and manage risks, optimize on capital, and make informed investment decisions and pricing decisions based on the simulation results, right? So there are real tangible benefits of running simulations, large-scale simulations for product development for financial services institutions. The financial services industry as such has long advanced grid computing. Some of the common patterns is over here, capital management and reporting. These are regulatory requirements that are they're mandated by law, where, for example, CCAR, solvency, and FRTB, these are some of the requirements to make sure they can do, again, there is capital stress testing that's done. We're going to be touching on that topic later. That's one use case. The second one is risk management. Again, portfolio simulations are central to running risk management by portfolio managers. They do that to optimize not only for opportunities, but also look for new opportunities and cost savings and any impact of hypothetical changes, be it regulatory changes or market conditions, and how to evaluate those effects on the workload, right? And then contract pricing and valuation. This is also very important use case for many FSIs, financial services institutions. This is to calculate and do simulations for credit and interest rate derivatives. And then finally, for product and strategy development. So there are real concrete use cases for grid computing that has been already being implemented in the industry today. This particular use case is going to go deeper into what are some of the complexities with running financial services modeling. So let's go one step deeper now. Now that we understand grid computing, HPC, and their use case in the financial services industry, why is financial modeling so complex, right? If you look at that, the need to conduct compute-intensive workloads, the calculations, the simulations in areas such as risk management, regulatory compliance, all these are not new to the financial services industry. However, what has changed in the recent past is the volume of data that they're dealing with and also increased timeliness of these calculations. So timely calculations with massive influx of data, that is causing a lot of issues with the on-premise grid infrastructure that you may have. I'll tell you some of the complexities here. So the first one is, again, I told you about the ability to run large-scale simulations for risk analysis models, right? When you're doing those type of modeling, some of the issues that the portfolio managers must be looking at is, well, what are the market risks? What are the credit risks and liquidity risks? In general, fluidity in the financial markets, right? So add that with the second variable being broad regulatory requirements. These are when there's CCAR. CCAR is a stress testing mandated by Federal Reserve to large American banks. Again, this is to test the capital adequacy. Same thing with Dodd-Frank. Again, Dodd-Frank is American legislation implemented widely. This is an offshoot of the 2008 financial crisis that led to Dodd-Frank Act. So, and then Basel III, this is solvency requirements for, this is an international framework that is implemented in the financial services industry. So you have these massive amounts of risk analysis that customers have to perform, add the regulatory requirements to the mix, and then you have to have the third variable in the complexity is, like I said, large-scale compute-intensive calculations that must be done in order to not just for existing products, but also developing new financial products, right? So if you add these three together, what happens is there is a massive amounts of compute resources that require to power these application workloads, right? And then to essentially to run simulations. So with wide variety of simulations, one of the patterns that we have observed is, again, let's say you want to do risk-based simulations for institution. They could do, one simulation method that we come across is Monte Carlo simulation, which is what Ben Liu and others have performed. So let's touch a little bit on that. What is Monte Carlo simulation? Now that we understand the complexity of the modeling itself, how is the modeling done through Monte Carlo simulation is the next point. So what is Monte Carlo simulation? It's a broad class of computational algorithms that are applied to obtain numerical results. Monte Carlo simulations are used to model the probability of different outcomes in a process that can easily be predicted due to the intervention of random variables. So that's the definition of Monte Carlo. There are multiple methods of Monte Carlo simulation. Essentially, it's a multi-step process. The first step is you will define what your domain of possible inputs are, and then you perform computations, large-scale computations on those inputs, and then you need to aggregate the results and then start ingesting those results for your valuations, right? So that is Monte Carlo simulation at a very high level. What are the applications for Monte Carlo simulation? Is it standard only specific to financial services industry? Not really. It has wide spectrum of implementations, physical sciences, again in engineering, microelectronics, to fluid dynamics, to telecommunications, and we just spoke about the financial services industry, so finance and business for risk analysis, computational biology, and there is also game simulation. So in artificial intelligence, Monte Carlo simulation is used for game simulation. One such implementation is actually used through tree search operation. So it's a wide implementation. This is not just specific to financial services industry. So now we have reviewed a lot. We reviewed HPC, then grid computing, and then we understood there is a complexity involved with financial modeling. And then within the financial modeling, we have seen one such use case, which is Monte Carlo simulation. Now that we understand what the business need is, what are some of the issues of running such simulations on-premise, right? The first and foremost issue that you run into running large-scale simulations is large capital expenditure. CapEx is a very big issue when it comes to grid infrastructure. Why is that? Because you would how many are familiar with grid computing? So yeah, so you probably have seen this in your own environments where large investments are needed to stand up grid computing infrastructure. Mostly, you would have a 2-year plan or a 3-year plan. You quantify your requirements, and then you start building your infrastructure based on the analysis that you have. And then what happens is you would have to continually iterate and maintain an internal SLA or an OLA to maintain the uptime of the service, right? So just think about for a second, if you're doing, if your requirement is you need to have a resilient architecture for grid computing, you would have to think about HA, right? HA clustering is key to that, making sure there is no single point of failure. When you talk about HA clustering, there is a lot of issues, there are a lot of variables that the data scientists may not be looking at, but the infrastructure engineers will be looking at. For example, what happens if my storage layer, the access to the storage layer is broke? So you would have to do some sort of redundancy there. How do people do that? Maybe if you have fiber channel arrays, you probably have multiple dual HBA cards running, right? And then if you have NAS devices, you probably have multiple NIC cards teaming, either NIC teaming or NIC bonding at the hypervisor layer. And then that would be connected to dual switches. Then that has to be through HSRP implementation. That's just two variables, right? And then you may have to do some sort of a disk mirroring for OS. A lot of overhead and a lot of heavy lifting just to support that infrastructure, right? And then there is limited capacity, right? I mean, this is, you have provisioned grid, and now if you have a necessity to scale, why do you have to have the ability to scale? Because as the market conditions are changing, there is always, and add to that the regulatory requirements to go back and do simulations for the last, say, X years. So you would have to ingest a large amount of data sets and be able to do simulations, which means you need to be having that level of expandability, the elasticity, and scaling options, right? That is one of the issues what we have encountered with customers having issues with on-prem grid, right? And then on-prem grid has certain cores. So if you are a smaller financial institution, maybe you would have 10,000 cores, CPU cores or so. Anyone familiar with over 50,000 cores here? So if you are a mid-scale financial institution, it is not uncommon to have a compute grid with 50,000 cores requirement, right? And then if you are talking about a global financial institution, it's not uncommon to have requirement for 100,000 cores just to run various risk analysis and simulations. So the point I'm trying to make here is when you have that complexity and when you have these variable workloads, you just cannot have a static grid with a static compute type, right? For the various workloads, some may be I/O intensive workloads, some may be CPU intensive workloads. So some workloads may require a lot of in-memory caching requirements. But then your on-prem grid cannot really adjust to all these computational changes, right? So it's a static grid unless you go through the refresh cycle every so often and update the grid with new compute and storage layer. So it's always a constant refresh cycle that you're, and also limitations that you're bound with, right? And then regulatory and market fluctuations, we did talk about that. Why is that important? Because that will change the amount of storage layer that you would have to configure, and also the amount of data that you're going to be ingesting into grid computing, right? So finally, all these issues end up with limiting your ability to run simulations because your data center capacity is limited. This is where it starts to hurt customers because they cannot, either they have to wait for expanding their grid computing framework, expand the infrastructure to support new workloads or increased simulations, right? So just look at some of the patterns. In a HPC compute scenario, what happens is you don't know what are some of the simulation requirements would look like because it's all variable based on the market conditions. On the x-axis here, I'm depicting here actual demand for compute. So your data scientists may be asking, hey, I need to run petabyte scale grid operation, grid simulation. So I would need so many compute cycles to run my simulation. And then on the y-axis, you have your provisioning, right, where provisioning times to increase your compute grid. So what happens here is, say you run into a situation where your on-premise grid is at capacity, and then there is new requirements to expand newer simulations or new product development, then you have to go through server acquisition and provisioning of new servers and attaching that to the grid and expanding the grid. So obviously, as you can clearly see, there are times where your projects could get delayed because of provisioning of the server infrastructure for an expanding grid. So that is one of the key issues what we have observed. And ultimately, what happens is adding capacity is both time intensive and capital intensive. So that has a direct effect for many customers, right? And grid users, which are typically the data scientists, seek the fastest possible time to results because they have a large data set that they have to worry about. So in the end, the jobs get delayed, the jobs get queued, and that will essentially throttle your innovation. That is the net effect of having limited grid capacity in your on-premise infrastructure. So with that problem statement, then we started working with customers, and we have seen financial services customers attempting to extend their existing grid infrastructure into AWS Cloud. So you still have your on-prem grid, and then now you're extending the compute capabilities into AWS. And how is that done, and why is it done, is what we're going to talk next. This is about grid computing on AWS. So by building and running compute grids with AWS, companies are able to leverage and execute a larger number of parallel tasks, which is very key. Like I mentioned, about the degree of parallelism has a direct impact on your simulations, right? And increase the speed and analysis and reduce time to results. How is that done? So let's talk about one by one some of the issues that we earlier discussed. So virtually unlimited compute and storage resources. You may have heard some of the best practices that we advocate is you need to decouple compute and storage. Not only that from a breakpoint analysis, but also to be able to scale independently of each other. And once you have your storage layer separate from your compute layer, you are no longer tied to idle time of compute. You could do variations in the compute and also variations with the compute types to achieve your processing needs. Various compute options. So this is very important. So as I told you earlier, with on-premise grid, you're essentially buying into hardware that you feel will be satisfactorily be able to apply all the computational needs, right? But then what happens is, as your workload characteristics change, you no longer will be able to change your compute infrastructure. That issue goes away with AWS because at the compute layer, you have wide variety of EC2 flavors, if you really need HPC clusters to be run on EC2. But on grid computing side, you can easily extend that to AWS Lambda. So that gives you a greater amount of flexibility, lower TCO, and not to have to worry about running and maintaining virtual machines and all the bootstrapping that has to go through virtual machines, right? So that's there. Cost optimization, of course, as I mentioned earlier, if you can execute the jobs by not have to worry about infrastructure, by abstracting the infrastructure, you are focusing on your core business development, your core product development, and let Amazon handle the server infrastructure for whatever HA or high availability requirements that you may have, right? Enhanced security. You can all extend, again, with Lambda, you can extend there is a wide range of security features on AWS that you could integrate with for whatever compliance and security needs that you may have. And then expanding big data capabilities. So once you have data in S3. Say, for argument's sake, you built a data lake on S3, and then you ingest the data, whatever mechanism, be it Kinesis, or maybe you're ingesting data through a private connection through a direct connect within a VPN overlay for encrypted data. Once you ingest the data into S3, you now have the option to do transformations on the raw data, and then essentially use that processed data to do whatever additional computation needs, not just simulation work, but you could actually extend that to business intelligence, like loading the data into Redshift for data warehouse, and then doing your visualizations, like say using QuickSight or Tableau or whatever data visualization techniques that you use, right? So you are extending that capability by just separating the compute and storage, and at a lower cost and performant. As you can imagine, S3 comes with 11 nines of durability, so you don't have to worry about how do I make sure my SLAs for my storage layer are met. Now, because now it is a managed service, you don't have to really worry about maintaining the storage infrastructure, right? And then automation capabilities. As you probably are aware already, these are all API calls. You could data scale. And there is concurrency that you can achieve with Lambda functions or auto-scaling in terms of EC2. And provisioning of resources becomes very easy just based on, again, your need, right? And ultimately, all these factors will help you with product development that is faster time to market, but also faster time for results for data scientists. The crux of the problem was, how do I get results faster in a cheaper way? And that is also extendable to other users of the same data set. So that can be easily achieved by leveraging AWS with all these various services. All right. Moving on. So now let's go more, before I get into the use case and the details of the use case, I quickly wanted to highlight, so what are some of the typical characteristics of grid computing? It's important to understand, first of all, you need the ability to host large data sets. That's where S3 comes into play. The ability to do resource sharing. Why do we have to do resource sharing? Because you may have raw feeds coming where the market data may be coming into your organization, and you may have multiple teams of data scientists who may be running different simulation jobs, different activities, right? So you need to be able to have that raw data be available to multiple teams to be able to do that. So the resource sharing is extremely important. And periodic and scheduled tasks, right? Most of these are, as you probably know, some market simulations, risk simulations that financial services customers do. These are not OLTP transactional type databases. This is, by the very word, it's analytical data. So you have large amounts of data stored and then run analytics on top of that, right? So you don't really have that transactional type workload. So you need to be able to do scheduled tasks, not real time in general. And then ability to do transformations, very important, because your simulations may, again, vary based on the market feeds and what type of simulation activity within Monte Carlo or any other simulation activity. Whatever your goal of achieving the data analysis, you need to be able to transform the data, the raw data. It may be as simple as converting your raw into ORC or Parquet or things like that, or just whatever the format that you're getting into a JSON doc or a text document, right? So those transformations are important for you. And usually some of the characteristics with grid computing is these are non-interactive, long-running simulation jobs, right? So with that characteristics, let's go into how do you implement Monte Carlo on AWS? So the key to that is you're leveraging the MapReduce framework. This is extremely important to do to run Monte Carlo simulations in the cloud. And to level set, what is MapReduce framework, and why is it important for Monte Carlo simulation? So the framework, again, here in the picture, this is an overview of the framework itself. You have a master node that assigns map and reduce tasks to worker nodes. As you can see, there's a splitter, which is essentially a bunch of input files, and then you get the mapper nodes take the data set, and then they process the data set. Input files are split into chunks and are processed individually by the worker nodes, and then produce a stream of intermediary key value data, which is again, which could also be hosted on S3, just like your raw files. And then records are selectively read by the reducer tasks, the task nodes, and then aggregated the results. So this is where the most of the transformations are happening, right? So this is a classic example of how Monte Carlo simulation can be implemented using MapReduce framework. So now, when we talk about MapReduce framework, the first thing a lot of you must be thinking, wait a minute, MapReduce for me means Redshift, EMR, and the entire Hadoop ecosystem, right? That is absolutely true. You could have Hadoop framework offer comprehensive solutions for big data processing, no question about that. However, if you think about the complexity of running a Hadoop ecosystem, there are a lot of nuances, there are a lot of coordination, there's a lot of bootstrapping that needs to be done before you could actually use it, right? Apart from the benefit of not having to manage any servers with a serverless framework, you would also have significant cost savings if you try to do this in a serverless way versus, say, running this on the traditional way, right? Using EMR, Redshift, and other variables. So this is one variation of the standard MapReduce framework. So on the picture here, you can see how you still have the same MapReduce framework that we discussed in the previous slide. You are extending that into the serverless side where you are ingesting the data, you're still storing in the input bucket, and you are triggering an event where there are mapper functions that take the data set, and then with Lambda, as I discussed earlier, there is no session state that you can store within Lambda, right? So you have to write it back to a persistent store. So here, there is a coordinator Lambda function in the middle. As you can see, the coordinator is essentially writing the session state back to S3, and then the reducer Lambda functions are, again, there is a concurrent Lambda functions that are triggered to take those tasks and essentially aggregate those results and write the result data set back into S3. So simple MapReduce framework that we discussed can easily be extended into a serverless design with this particular framework. Again, what are some of the goals of why do we have to stand up something like this? Well, what am I achieving by doing that? Is essentially abstract infrastructure management. If you are a data scientist and you want to use, say, the traditional approach, then you would have to understand the Hadoop ecosystem, how to use EMR, right? So unless, and there was a ramp up to that too, right? With serverless framework, what you could do is, first of all, you're abstracting the infrastructure management and almost close to zero setup time. You could essentially wrap this whole thing into a CloudFormation template and create multiple environments for your different teams for them to do analysis and still have access to the same data set. Why? Because you're essentially using the same raw data set that is on S3, right? And then you can do access management, the identity and access management by extending your corporate SSO with IAM roles and essentially doing assume role to give specific permissions to your data scientists or users. So that's the implementation for this specific task. On the same pattern, this is the pattern that Fannie Mae has implemented, which Ben and John, they have extensively worked on implementing. So this is a small variation of the one that we discussed earlier. Here, as you can see, there is S3 input files. The raw files are inputted into S3, and then there is an EC2 splitter function. Then you may have a question about why are we doing a EC2 splitter function? Because at the time, again, there are large data sets that were coming in. And as you probably know, Lambda has an execution timeout, so it has to complete within 5 minutes interval. Some of the splitter functionality was extending beyond that timeout threshold. So to work around, the workaround was use the EC2 as a splitter function, and then ingest that into, after the large data sets are split into multiple chunks, the smaller chunks are inserted into S3 bucket, and then your MapReduce activity is triggered through Lambda functions. So I hope that makes sense, the difference between why EC2 splitter versus the previous slide where it was purely serverless. So it all depends on, the idea here is based on your workload characteristics and your data set size, you can easily change the architecture and do essentially MapReduce activity in multiple ways, and you can achieve this very easily and in a repeatable fashion. And so we discussed about the compute portion, but what about we did talk about the regulations, right, and security concerns, or how do I protect my data? Not just financial services, but other customers too in other industries have questions about, okay, I may be carrying NPI data. NPI stands for non-public information, or PII, like publicly, personally identifiable information. Very critical. This may be confidential data or highly confidential data. So if you have classifications like those, and you want to be able to make sure you are securing the data, you can easily extend that through a AWS KMS. It's a key management service. If you have any compliance requirements, you can, for data encryption in transit, like I said earlier, you can always do VPN over DX to encrypt your data in transit, and encrypting data at rest can easily be achieved through KMS keys, right? CloudWatch, again, extensively used for not only monitoring, but also triggering events. And all this end-to-end solution can easily be treated as an infrastructure as a code through CloudFormation templates. Very easy to duplicate the environment and recreate as necessary. And then CloudTrail, if you have, again, you may be interfacing with auditors, both internal auditors, external auditors, and they may have questions about who had access to this data, who manipulated the data, and what are the API calls that were used to manipulate the data. So if things like that come up, you can easily use CloudTrail, which will help you identify those API calls, and you can integrate CloudTrail logs. There's a wide variety of implementations, both in-house and also third-party solutions or partner solutions that can actually be leveraged to alert back on-prem. And then you can control the access to the data set itself at a very granular level through IAM. There are many implementations, both IAM roles and resource-based constraints and things like that. So that's a holistic view of how you can maintain and manage your grid computing infrastructure. The slight variation here, the previous one was the splitter functionality. Here it's batch processing. The only difference being the mapper results are inserted into the DynamoDB table here. So just a different perspective here, a different architecture. You can easily extend that. The same thing, again, carrying on with the theme. There is, if you have any real-time file processing that needs to be done. Another method is, again, you use S3 as your data lake, your ingest point, and then you trigger an SNS notification that will essentially invoke Lambda functions from there. And then the rest is the same. You could, the persistent store could be Dynamo or S3, right? So quickly, we're almost coming to the end of the first segment where Lambda considerations. are important for your grid computing framework, right? So some of the important data points here are functions or a unit of deployment. So you can scale per request and never pay for idle, and skip the mundane activities like maintaining servers, patching servers, be able to maintain your container environments and things like that. So you don't have to do that, right? You can provision this on the fly, meaning we take care of that from the AWS end. All you have to do is to maintain your code set and focus on your business deliverables instead of the infrastructure, right? So that is what is essentially the key to this. Again, like I mentioned multiple times, do you remember AWS Lambda is stateless? So if you have any state information that needs to be handled, then you would have to write to a persistent store. The execution environment that your Lambda function is running in, it will not stay persistent, right? So you need to keep that in mind. So this is a container environment, but that container will go away or might go away in the subsequent invocation. So you have to think about, if you have state information requirement, write it to a persistent store, bottom line, right? And then for low-level ETL tasks, you can use on the container itself, you get access to a temp file space. You could use that up to 500 MB for low-level ETL before writing the results back to your persistent store, right? And then, like I mentioned earlier, a broad range of options that you have to control any security concerns that you may have. We have a robust set of security tools to help you manage the boundary. And if you have to run your workloads inside a contained environment, inside a private, most of the customers also I have seen where they want to run their workloads in a private IP space, right? So you could extend that RFC 1918 address space, which you're already using internally in your production fabric, onto AWS by creating private subnets and routing the request through your DX connection or VPN connection to your VPC, and execute Lambda functions inside your VPC through ENI, right? So if you have such requirements, it's very easy, very extensible framework, the one that we spoke about. With that, I will hand off the mic to my co-presenter, Bin Liu, who will walk us through Fannie Mae's use case. Thank you.
Good evening. My name is Bin Liu. I'm Director of Risk Modeling and Analytics at Fannie Mae. I'm going to talk about high-performance computing using AWS Lambda for financial modeling. Fannie Mae is a leading source of financing for mortgage lenders. We provide access to affordable mortgage financing in all market conditions. We effectively manage and reduce risk to our business, taxpayers, and the housing finance system. Fannie Mae's credit portfolio size is about $3 trillion. Financial modeling is a simulation process to project future cash flows. Fannie Mae uses a financial modeling process for managing mortgage risk on a daily basis. We use it for mortgage underwriting, valuation, risk management, financial reporting, regulatory reporting, loss mitigation, and loan removal. Every month, we generate more than 10 quadrillions of cash flows in hundreds of economic scenarios. High-performance computing grids is a key infrastructure component for financial modeling. Fannie Mae's existing high-performance computing facility no longer meets our growing business needs. It is more than 7 years old with limited I/O, compute, and storage capacities. It has complex distributed computing API for application development, and it is very costly to maintain and to refresh. It takes more than half a year to add any incremental computing resources and deploy any new application. We were looking for a new high-performance computing facility that enable us to react to the rapidly changing market. We want to have access to unlimited compute resources and unlimited storage. We want the facility to be reliable, easy to manage, and stay current. We also want the facility to be cost-effective. On the application side, we want the facility to provide simple distributed computing APIs. We want to be able to maximize reuse of our existing code base, and we want to be able to deliver the new solution in short time. AWS serverless computing offers the ideal solution to the new business requirement. Fannie Mae began to build the new high-performance computing platform using Lambda in 2016. This is the first high-performance computing platform using serverless architecture in the industry. It is also the first pilot program at Fannie Mae to build this cloud-native application. Since Fannie Mae is in a highly regulated industry, it took us more than half a year to build the infrastructure that meets our information security standard. Once the infrastructure is constructed, we were able to deploy the first working prototype within a month. In March 2017, we deployed the first financial modeling application to pre-production and ran on 15,000 concurrent Lambda executions. And in June 2017, we completed our production migration of the first 4 financial modeling applications. This is a performance testing result of our new serverless high-performance computing platform. We ran one simulation of approximately 20 million mortgages on 15,000 Lambda executions. It took 1.5 hours, which is more than 4 times faster than the existing process. The Lambda service provisions 3 Lambda executions instantaneously at the start. It then automatically provisions additional 12,000 Lambda within the first 50 minutes. The performance of the Lambda does not degrade during the ramp-up time. As you can see on the chart, the Lambda invocation rate increases linearly as a function of time. The Lambda CPU efficiency is close to 100%. The actual elapsed time is consistent with the estimated elapsed time based on Lambda billing time. This is a reference architecture for the simple parallel process using Lambda service. MapReduce framework is used for managing the high-performance computing workload. Serverless computing is event-driven computing. The central idea here is to leverage Lambda capability to perform the map function and automatically execute n copies of code simultaneously based on input events. S3 is used to store the input events and output data. We divide the process into 3 functions: splitter, mapper, and reducer. EC2 is used to split the input file and write n triggers to S3 event bucket. The mapper is to perform the distributed computing. Lambda is used to automatically carry out n executions and write output to S3 mapper bucket. The reducer is to aggregate the output data. EC2 is used again to aggregate the outputs and write final result to S3 reducer bucket. We can decompose complex workload into multiple simple ones. for parallel computing using Lambda service. Athena is also a good serverless tool to aggregate the output data. There are many benefits of using serverless high-performance computing platform. First of all, it is cost-effective. We never pay for idle. The cost is based on actual vCPU usage in the unit of 100 milliseconds, not the elapsed time or maximum processing capacity of the infrastructure. We can achieve performance at zero cost. For example, the cost of running one Lambda for 15,000 hours is the same as the cost of running 15,000 Lambdas for 1 hour. It also shortens the time to market. We're able to burst to cloud immediately to access additional cloud computing resources. We're able to focus on our business need. There's no server to manage and no complex distributed computing code to write. AWS ecosystem also provides a streamlined integration with big data analytic platform for data mining and machine learning, for further analysis, visualization, and reporting. The following are best practices for running high-performance computing workload using Lambda service. First, we need to break down complex business logics into multiple simple ones for distributed computing using Lambda service. We need to maximize S3 performance by evenly distributing the key names of the objects. We need to set up a separate Lambda account for unlimited access of the resources without running out of IP addresses. We also need to adopt microservice architecture to migrate one business application at a time and integrate with AWS code pipeline and SAM for CI/CD and DevOps. Fannie Mae is planning to complete migration of major financial modeling applications to AWS in 2018. Thank you.
So quickly, I wanted to showcase, so you can extend this framework that we talked about, how Fannie Mae has implemented this solution. You could extend this framework to your own environments. And there is actually a blog post that we published. The information is there in the appendix. You can get access to the slides to get more information on finding the blog post. So quickly, I wanted to showcase some aspects of running this. There is also, the code is published in GitHub. You can clearly access and the code and download the configs and run this and extend this framework. One important feature that I wanted to talk about is, again, you need to write very simple. This is extremely easy, very easy to replicate in your own environments. A simple creating an IAM policy here, giving permissions for the Lambda functions to do two things, right? One is access to the S3 bucket. The prefixes are defined through internally in a JSON document. And then you are also giving permissions to create the log stream, right? So you're giving access to the log stream, and then you are creating this role. And once you have the role defined, you can go to your Lambda function, and essentially I'll give you an example on how it looks like. And essentially you're defining your execution role right there. That is how you are giving permissions for Lambda, the big Lambda role. And then you are managing your environment by giving the memory that it requires to run, and also setting the threshold for timeouts. So that's as simple as that. You could extend this framework and write your own code, or essentially duplicate this MapReduce framework with Lambda that is available on GitHub to get results that you desire. And just looking at some of the CloudWatch metrics, here is some information. When you run that code, you essentially get access to, you can quickly review some of the details that is published to the log groups, the CloudWatch log groups, as part of the Lambda invocation itself. So you can actually see the invocation, and as the mapper function and the reducer function are working on the splitter files, and then writing the processed files back to the S3. You can actually see that in the log groups, right? And then finally, I just wanted to do a quick wrap here. So Lambda servers, again, just to wrap up, it can be extended to the MapReduce framework. Some of the advantages here is you can trigger events, no servers to manage, flexible scaling, no idle capacity. You're not worrying about spot instances or reserved instances and things like that, right? High availability. I discussed extensively how difficult it is to maintain HA on-prem. You're essentially offloading that heavy lifting to AWS and focusing on your code, your development efforts, and your business outcomes, right? And then you can bring your own code. You can also, again, those are language support. If you have any libraries, the custom libraries that you may have, you could leverage custom libraries inside Lambda functions. And pretty simple resource model that we have already discussed with respect to just two variables, your memory requirement and your execution timeout, right? And then we discussed about programming model with Lambda and the statelessness and how to maintain session state and things like that. Monitoring and logging is extensive. They're all built-in metrics that you could leverage. And authoring functions is pretty straightforward, and whatever execution environment that you're already familiar with, you could use that for that. Event sources, the list will continue to grow. These are just a few of the event sources I have listed here, but these are many standard implementations for grid computing. We have seen a large implementation with S3 as the data source. But don't be under the impression that this is just for S3 based only. You can extend this framework. A lot of AI and machine learning also it has been integrated. Again, API gateway is a common source too. So please do review some of these characteristics, both from a functional standpoint, what your grid computing can do for you, and also from a technical standpoint on how you can extend this framework in your own environment to get the results that you're looking for. So with that, we conclude the session, and please complete your session evaluations, and hopefully you can implement something similar in your environments, and hopefully next year we'll be talking about your use case and your success story. With that, it's a conclude, and thank you all for attending this session.